Thank you, Diane, for the introduction, and thank you to the organizers for inviting me to the talk. Toric interpolation is something, it's not a standard term, so it was invented by my co-authors and me. So in lack of a better name, I can explain what it is. So the plan of my talk is first I'll tell you something about toric varieties and lattice polytopes. From this you understand that I will define embedded toric varieties in projective space. So they can be defined by lattice polytopes or by the lattice points, not necessarily all inside the polytope, but at least some of them. So I'll get back to that. And second point will be to define what is called osculating spaces. And for those of you who do not know, these are higher order tangent spaces. So you all know what a tangent space is. And if you differentiate further, you get high dimensional oscillating space.
Are these the same things as jet spaces?
Yes.
Okay.
Well,
almost.
Okay. But let me just put it like that. They can be defined by bundles which are in differential geometry, called jet bundles, in algebraic geometry, or something else, which I will also get back to. And then I will say something about interpolation problems, because I have to at least justify somehow why we call it toric interpolation. And finally, I will show existence and uniqueness of toric interpolants. And those will be toric varieties that interpolate a given toric variety. I will explain. So this is just the outside. Now I have to it's not so good. Let's see how it goes. You probably cannot even see it. I'll get to it. Okay, so let's start with toric varieties. And so Piene will be complex projective space. It's not necessary to work over the complex numbers, but this is what we did in our joint work. So I will just take projective space, and the points will be denoted like this. So this will be the equivalence class with respect to multiplication by a non-zero scale, as we have seen, not just last, even in the last talk yesterday. So I will not say more about that. But now, suppose I'm given n plus 1 lattice points. So I'll be in set n. So it's not the same. This will be smaller than n, but it is smaller than equal to. And then I can define a map from C star m to torus, m torus, to Pn by sending an m tuple to T0, T m, and here this means T1 to the first thing here, then T2 to the second, etc. So this is just, these are just monomials. So I'm just looking at the monomial map. But which monomials are defined by my lattice? And the closure, sorry, it's nailed down. M, that we'll call X, is toric variety. And if you have any other definition of a toric variety, that's fine. And for this talk, you only need this definition. And there are actions by the torus, which I will get back to, but that's, for the time being, this is just enough. So it's, in some sense, it's just the closure of the image of a monomial map. Maybe the easiest way to define a toric variety. Now, let me just give you a simple example. Oh no. Here we have Z. We have 1, 0, 1, 2, 4. So these are 4 lattice points. So it gives me a map from C star T3 by sending T to 1 T TQ T4. And it almost looks like a twisted cubic, but it's not. It's a quartic curve because if you take the plane and intersect with the image here, you will get 4 points. So it's a degree 4 point. It's a quartic rational and toric curve. And it is not non-singular. So my toric varieties can be non-smooth because it's going to have a cusp. That's okay. And let me just now say that if you have this missing lattice points. So if you take the convex hull of your lattice points here, you take this, and if you now look at the intersection of the convex hull with the lattice, you will get one more point. You'll also get this point. And that will give you a different map. You will add and this you will recognize is the rational normal quartic curve. And in fact, I'll get back to that, but in fact, this curve is just the projection of that curve from a point which is not on the curve. So you keep the degree, but so it will be projected from 0, 0, 0, 1, 0. So this is how you can see your lattice points, and you can do some geometry thinking by, for example, projections. We'll see more of that. I'll give you one more example. So now I'll do m equals to 2, m is 5, and I will take 1, 2, 3, 4, 6. So these are my 5 points. And so I have A0 is 1, 0, A1 is 0, sorry, 0, 1, and then A2 is 2, 0, A3 is 0, 2. And then what do I not have? I have A4. It's 2, 1. And A5. 2, 1. So what is the convex hull of this thing here? It's a hexagon. And what you observe is that, so if you do, so the map now is defined by sending T1, T2 to T1, T2, T1 squared, T2 squared, T1 squared, T2, T1, T2 squared. Okay, this is how it goes. But you see here is a missing point. So if I instead do all the lattice points in the convex hull of my given lattice points, I get an embedding. Here I get something into one, two, three, four, five, six, so into P5. But if I instead include this point, I get something into P6. And again, this surface here is going to be the projection, a linear toric projection from the point corresponding to this point in the new embedding. And I will get back to this example so this can stay for a while. So now I'm going to define a matrix, which is just the matrix of the lattice points with an addition. So I have my lattice points. And I define matrix A, which is going to be, sorry, I can just write it like this, 1, 1, 1. So I put ones in the first row, and then I do these lattice points as columns. Okay. And I'll denote by XA, the toric variety. Defined by these lattice points. Just as I did before. So I can sort of go from lattice points to an integer matrix, and I always have the ones in the first row, and then I have just lattice points here. And this machine happens. One. So Pn has a diagonal action by the torus, the n+1 torus. XA is going to have an action of Cn, C star n, given by these lattice points. So maybe I should just say that. Note that there is a C star n action actually on Pn, defined by sending P1 Pn Xn to what you think T A0 F0 An Xn, and then what you see is that XA, it's just the orbit of the point 1. So we have, first, inside XA we have the torus, and we embed the torus into Pn, and we take the closure. and you can view that as the orbit of the point 1. This is all standard. Let me just say something more about XA. So the dimension, sorry. I'm the first. This happens. What should I say? Facts. Dimension of XA is the rank of A minus 1. I want to say if P is the convex hull of the points, of my lattice points, then I can let n prime be the number of lattice points in P. So you've seen in both my examples, there was one sort of missing lattice point. But if I take all of them, I can define XP to be XA prime, where A prime is the matrix obtained from all the lattice points here. And what you then can see is that the dimension of XP is the same as the dimension of XA. XA is a toric linear projection of XA. It lives, this XP is going to live in this bigger lambda. And what else do you want?
Sorry, at the bottom, one of these should be a P.
Sorry?
Should one of these be a P at the bottom?
The projection of XP. Oh, sorry. Absolutely. Thank you. I'm glad some of you are awake after your evening. Okay, what do I also want to say? I want to say that the degree of XA is the same, and since this is not an arbitrary linear projection, it's a projection, I'm not sort of touching the vertices on my thing, because P is the convex hull of my given point. So P has the same vertices as, I mean, when you project, you're not changing things very seriously. So this is going to be the same as the degree of XP, and which of course is the same as the lattice volume of the polytope P. So here you have 1, 2, 3, 4, degree 4. In this case, you have 1, 2, 3, 4, 5, 6. So the lattice volume here is 6. If you include this, it's still degree 6. You don't change the degree. We've seen that. And now, now I want to actually, I think, erase here and just, this is not maybe very relevant, but it's a nice way when you're looking at toric varieties coming from polytopes. It could be nice to see how projections and sections work with respect to the polytopes. So if you instead of, now I'm going to look at, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what does this? Anybody know what's the variety here? It's a simplex, but three times the simplex. So
By over 3.
precisely. So this is the third Veronese of P2 in P9. Now, what can you do with it? You have a surface you can project, but this time you can remove vertices. And this corresponds to blowing up the point. And I'm not going to go into that, but that's in this dictionary we have. You remove a point. And then you see you're left with this thing. And you still have this. So this red thing is what we saw over there. If we include this point, we get the Del Pezzo surface, degree 6 in pieces. And now you could do something else. So who knows what this is? Square, twice the square. You probably know.
1 cross P1 embedded by over 3.
So this is the Segra P1 cross P1, not in P3, but in 1, 2, 3, 4, 5, 6, 7, 8, 9, P8. So it's Segra with O, with O, 2, 2. But now again, if you want to project, you can take away this one and this one. And you get again the Del Pezzo surface. So you can view the Del Pezzo surface in 2 ways as projections, one from the Severi, one from the Veronese, and the other from the Segra. And I'm going to give you one more, which is a little bit harder to visualize. Use your imagination a little bit. So this is just a cube. So one cube. And now so this is again the Segra, but now with all 1, 1, 1. And so it's of dimension 3. And now what for lattice polytopes do sections correspond to? It's sort of dual to projection. So actually, if you want to take a section, you have to collapse this thing because you need something of smaller dimension. And what you can do is identify, you stand here and you look at that point and then you just smash everything. And what you get is a picture like this. So this is again a way of obtaining the Del Pezzo, but now as a section and not as a projection. You can play around with these things, and that's. Oh, I have to move on. This is more fun. So let me briefly say something about osculating spaces. So just to give you the idea, let's take a curve in space. You have a point. Let's say it's parameterized for a variable t. You move. Here you have the tangent direction. So what is the tangent line? That's the line spanned by this point and this point. But you also have acceleration, so you have a second derivative. And what is the osculating plane? That's the plane spanned by these two vectors. So that will be the span of this point, and this point, and so on. So in general, if you have x in Pn, and suppose dimension of x is n, and you can assume that you have some local, or actually, in our case, just go back, think about Toric varieties. We have a nice global, almost global parameterization. So just think of T1, Tn, those two. Here, in our case, these are just monomials. They don't really have to be. We want to define osculating spaces. And now you do the same thing as here. How do you get the tangent space? You take the span of this point and all the partial derivatives with respect to t. Tangent space is just the span. Oh, I will just write this as xt. So you have xt, you have d t1 xt, d m xt. So you have m plus 1 points, and it gives you an n-dimensional space. In the case that is the dark varieties. As long as t is not 0. No t's are 0. And then define the case osculating space by the point corresponding to t to be the linear span of, you have the tangent space, and then you take all partial derivatives of the t's up to order k. So this will just be d I, whatever. Okay. Yeah. Let me just write this. All partials up to. So it's just like in this example here. And the dimension, we get an upper bound for the dimension in terms of the dimension of x, but it's not always equal to this upper bound. It depends on the day. Now, let's write the spaces in terms of a matrix. So let's write A, K at the point T to be, sorry, ordinary x0 t, xn t, and then I do the partial derivatives. And then I do all the higher order. That means higher than 2 partial derivatives. So then what you see is that now the kth osculating space is just the row span of this matrix. And the dimension of the kth osculating space is going to be the rank of this new matrix minus 1. But it's not an important deal. Let me just remark that, so now I have for each point T1 to Tn, I have defined an oscillating space. So I have sort of a family of oscillating spaces, and these spaces can be encoded by a sheaf, which is jet sheaf in differential geometry, but in algebraic geometry, it's called the sheaf of principal parts of the line boundary O1. So please note. What should I say? Are defined by the sheaf of principal parts. I'm not going to use it except that it exists. It's EGA stuff. If you look in the volume 4 of EGA, you'll find everything you need to know and more. More than you need to know. P, K, X. And this is 1 because I'm taking principal parts of the line boundary of X, which is just the restriction to X of O1 on P. And the point is that we have a map, sheaf homomorphism with all kinds of nice properties. And if you look at the image, then because this could have higher rank than the actual image, which means that the oscillating spaces are not sort of maximal dimensional. And this will be the fibers here will give you my oscillating space.
Question?
Yeah.
So this is only defined on the image of the torus, right?
This is now defined on the image of the torus. I also have principal parts of the torus.
But X is the closure of the image.
It's the closure, but it's defined on the closure. Yeah. So in case of toric variety, this is defined on X. But it's not necessarily, the spaces may change at the boundary of the toric variety because those may be singular. Yeah, so now I think you can do as exercise the rational normal curve. You can write that. It's easy to see what you get as the matrices. You have a very easy parameterization and you just differentiate. I should maybe say one thing, that because of the way, because of this definition of principal parts, bundle or sheaf, the derivatives here are actually Hasse derivatives. And it just means that you divide by some factorials, and then you take the usual derivative. The Hasse derivatives work better in characteristic P. In characteristic 0, this doesn't really matter. But if you want to see you want to have this nice version here, it's actually the positive derivative, because it has to do with Taylor expansions of functions. But I'm not going to go into that at all. Yeah, so I want to say one more thing here, because you can do yourself as an exercise. You can compute the second osculating space to the del Pezzo surface, which means that you include this, and you're going to get 5-dimensional spaces. If I remove that and go to the projection, I get what is called the Togliatti surface. And for the Togliatti surface, the dimension of the osculating space, it lives in P5, and the dimension, expected dimension of osculating, second osculating spaces for a surface is 5, but for the Togliatti surface, it's only 4. And the reason is that if you look at the del Pezzo surface, the osculating spaces all go through the same point. And this is the point corresponding to this point. And when you project from that point, you lose 1 dimension for the osculating space. So this, all this you can compute, and it's a nice exercise. Okay, let's move on. This I can probably just maybe write too much. So what is the classical algebraic geometry? Classical interpolation problem in algebraic geometry is, for example, look at hypersurfaces of a given degree and ask how many points can such a hypersurface interpolate. And to interpolate points just means to contain them. So, of course, the superclassical problem, going back to Ragni, is to ask how many points can a plane degree D curve interpolate. It just means to contain. And I think you all know the answer. The space of plane curves of degree D is D plus D over 2. And to go through a point is a linear condition in this case. So if the points are in general condition, the maximum number you can interpolate is D plus D over 2. And I should just mention that sort of the final answer in some sense to this case, when it comes to curves, is the work by Erik Larsson and Isabel Vogt, who solved the sort of Brill-Noether interpolation problem. And they found the maximal number that the Brill-Noether curve could interpolate. And I'm not going to talk about this at all, but I do want to mention it. So in some sense, this old problem is maybe, I guess one can say, is settled. Now, I need to say something about different kind of problem, which is our inspiration. And that doesn't have, it's not about points, it's about linear spaces or families of linear spaces. So for example, if you have C, the plane curve in Euclidean plane, it will have, of course, tangents, but it will also have normals. So every curve, you have a tangent, and then you have a normal. And now you can ask, can you find another curve which has these normals as tangent lines? And curve, let's say D, such that tangents to D is normals to C? And the answer is yes, you can. And it's called the evolute. This is also super classical. And just to give you one drawing. Here you have C. And then you have the center of curvature here, center of curvature here. If you look at this point here, you'll have the center of curvature somewhere here. If you look at this part, you will have a center of curvature here. And in fact, the evolute is going to be this curve. And the points here corresponding to these are what is called the vertices of the given curve. So you would think these are the vertices, these are the vertices. And it's a 4-vertex theorem, which you can also look at. But this is a sort of classical example of an evolute. And one can say, if one wants, that in fact the evolute interpolates the normal lines to C, because interpolate does not mean to contain, but it means that these lines are as close to the curve as possible, namely their tangent lines. And you can do this also for a space curve, and then you can ask for the normal planes to the space curve. Instead of the normal line, you will have a normal plane, and you can ask for a curve which has these planes as osculating planes. And then you get what's called the space evolute. Yeah, maybe not. But now let's so given a space curve C in R3, so again we're in the Euclidean space, so that we have perpendicularities, we know what the normal plane is. And you can ask, does there exist a surface now such that surface containing C such that the tangent space to Y at the point X is equal to sorry, I don't want that. No, I want that. I want the osculating I want the osculating plane that you see at the point X for X and C. So the points on X on C are also on Y, and I want the tangent plane to the surface to agree with the second osculating plane to the curve. Only along, we don't know what happens elsewhere, of course, but only at. And this is now what I'm going to continue with. So, what are the Toric? So this, you could say that Y is an interpolant, the second interpolant of C. Let's just given the definition of the Toric interpolant. So if X is Toric, sticking to my dimensional thing, the dimension of X, whatever, K is some integer at least 1. If I take the first interpolant, I just get this variety itself. We will see. I can now K, and then we say that the K Toric interpolant of X is a toric variety Y. X should be contained in Y, and such that the tangent space to Y at X is the case oscillating space, to X at X for almost all. It turns out that if this exists, then this equality and this almost all precisely means on the torus. So that's the open days. Almost all. And so, as I indicated in my beginning, what we then show is that okay, toric interpolant not only exists, but is real.
Yeah, I'm confused about the definition. Like, in your evolute curve, the points are not the same. So I thought that there exists another point on the evolute curve such that.
No, so I'm not saying that it should be the same points. I mean, I'm just saying that.
But here it is.
No, this is a different definition. This is not an evolute.
It's a different.
Yeah, I mean, just to make
Okay.
it's a completely different, it's a very different notion of interpolation.
Okay.
And so our interpolant is not an evolute. I think I first called it the toric envelope, and then I realized that envelope was bad because that had a precise meaning already, so I didn't use that, which is one of those are an evolute. So we have to find something else. So I think, given the time, I may give you, we'll actually start by giving you the super simple example, and then you will actually be able to see how you construct the interpolation. But let's get back to even simpler examples than the quartic hospital toric curve, but let's just take it as it is. And then you will see. So if I do this matrix, recall that I have, this is my parameterization. Now I take differentials with respect to t. I only have t. So it's easy. And then I want to take second derivatives. And so the row span here is the tangent vector. And now I add the second derivative. And you see I do the other thing here. This is what I get. And the row span here is going to be the oscillating plane at the point corresponding to it. And now, if I look at A2, 1, I get the matrix 1, 1, 1, 1, 0, 1, 2, 3, 0, 0, 1, 3. So this is a very nice lattice thing where I have my ones, and then I have 1, 2, 3, 4 lattice points, but now in 2 dimensions. So I can consider XA2 That's going to be the image of, I have to have a new variable. So I have sort of my variable for this row. So let's introduce new variable u for the third row. And then you see that this will be the image of closure of the image of u going to, sorry, what do I do? I here, no t's, no u's, so 1. And then I have t squared u. And then I have t cubed u cubed. So I can, sorry. I have this lattice point, 0, 0, 1, 0, 2, 1, 3, 1, 3, 3. These are my lattice points, and I can
It's right here.
What? Okay. You see, missing lattice points. So this is what will often happen. You don't always get, if it's a convex hull, you don't always get all the lattice points. So this is just going to give you a surface in 1, 2, 3, 4, minus 1, 3 space, which is what you expect. I mean, you're looking for a surface with this special property, and it's a surface of degree 1, 2, 3, 4. So the claim here, of course, is that y, which is x and is the second toric interpolant of the twisted cubic. And now you start to sort of degree is 4. And for those of you who know something about the twisted cubic, maybe you know that it's tangent developable. The surface generated by its tangent lines is also a degree 4 surface. So you might think, why do you have 2 degree 4 surfaces associated with the twisted cubic? And of course, the tangent developable is not a toric surface, nor does it have the property that I asked. It has, I was not going to say the opposite, but it has the property that if you're on a tangent line to the curve, the tangent space to the tangent developable is the second is the osculating plane of the curve. But this does not happen at points of the curve because the curve is a cuspidal edge of the tangent developable. This is I won't go more into that, but you can compute and yeah, probably. Now I have like 7 minutes or something like that, I think. Let's see what I can do. So now, so in general, you do the same thing. So the existence you construct A, K, E, and you define Y to be X, A, K, where now A, K is just A, K, where you put everything equals to 1. So then you get an integer matrix, and you can take its toric variety, and then you have to show that this is precisely the same. And when you construct this, you see you have, let me just actually go back here. I construct this, I get a matrix by putting everything equals to 1. And then I have to introduce new variables. So first I have my old sort of matrix A, and then I have to give variables for each new row. I will get a lot of rows. So for each row, I have to have a new variable, and I have to have the power of this variable determined by my matrix. And you see, when you do this and you look at the tangent space to y, you get precisely what you want. There is some multiplication by the torus action, but as long as all the t's are non-zero, things work out well. You're not changing the values. So I think this is actually as much as I should say about the construction. And then for the uniqueness, so you assume XB is another space, interpolant of X, and XA, and basically you have to show that P is equivalent to this new matrix AK in some sense. And first of all, you have to know that P can be taken to the other form also once, and then something here. And the fact now that you have two families of linear spaces along XA, or at least on an open dense of XA, which are equal on an open dense again of that. And if you have two such families that are equal on an open dense, they're equal everywhere. So at least on the torus part, you get equality. But that means that maybe I should say, so this just implies that, this is what you need to show, that tangent space to XP at 1 is the same as the osculating case space to XA at 1. And this implies that the row span of B is equal to the row span of, of X, this matrix AK, which defines the osculating case space at the point 1, 1, 1. But if these row spans are equal, then they're affine equivalent, and so you get, in fact, XB equals to X. Just want to mention one more thing. If you now, I mean, as an exercise, you can compute the toric interpolant of the Del Pezzo and the Togliatti surfaces and see that one is a cone over the other. But this I want to do. Let me just say that in case of no, I have it here. Maybe I'll just stick to if you do the rational normal curve of degree n instead of the twisted cubic, you will get a similar situation. You get a very nice, this will be part of it, and then you will go on and on and on. And these things here will be examples of use fancy, especially those who are in Leipzig, notation. So these are examples of generalized tree amplitude and of type A for general n, type n plus 1, 1, 2, Z, where Z is a positive matrix, and in fact Z is just our agent. And in particular, gives rise to a positive geometry. And then you're over in scattering amplitudes and you can play with these things in other settings. And, yeah, let me just say that if you want the full proof, just look up our paper. And it's completely open access. You can just Google it. I think I'll just stop there.